Today we're going to be continuing on from the last lecture. We sort of did a jump start on heaps, and I'm going to go here today. So for those of you who might have forgotten some of the stuff from COM 210, there should be a bit of a revision as well, and then we'll go on to some aspects of heaps. So I have the following slides from the last lecture, speaking about back to comparison sorts. And this time, the only difference is now we're actually going to be using a data structure, heap data structure for doing the sorting. And we're also going to hopefully add priority queues, which is a slightly different topic. If you have we spoke about the property of two types of heaps. You can have a min heap, and they're essentially very similar. If you just turn the logic upside down, everything else remains the same. Okay, and that the heaps are have the following two properties. Each node is bigger than or equal to its children if it's a max heap, and if it's min heap, it's just the other way around. And the height of the subtrees will differ back most to 1. Okay, and this is generally it generally uses what is referred to as a complete binary tree. Okay. Now, for those of you who don't remember your complete binary tree from a perfect binary tree from a full binary tree, this is just a quick recap. So a perfect binary tree is one which, as you can imagine, is completely symmetrical, as it seems perfect. It's got all the nodes in there. However, a full binary tree may be a little confusing. Well, a full binary tree is essentially one that has every node is either has 2 children or has 0 children. Okay, so you can see that it's not perfect in the sense that some of these nodes don't go all the way down to the bottom, but they do satisfy the property that either they have 0 children or they have 2 children. They can't have 1 child. Okay, and a complete binary tree is different from a perfect versus a full binary tree in the sense that at every level except possibly the last, it is completely filled, and all nodes are as far left as possible in the last row. Okay. So the first question that I would like to sort of make you guys think is that we said a heap is represented by a complete binary tree. Now, for those of you who have, I'm sure all of you do remember some of the stuff that we studied in COM 210, we've studied. Why do you think that we're representing heaps using a complete binary tree? You know the properties of a complete binary tree? So why use a complete binary tree to represent a heap? Why not, perhaps, clearly you can't use a perfect binary tree, but why not maybe a complete, why not a full binary tree? Or maybe one which is not a complete binary tree, but perhaps these nodes are not shifted all the way to the left. Okay, why do they have to be shifted to the left? So yes. Yeah, so essentially what we're saying is that while a heap does not have to be represented by an array, it could be represented by a tree. However, generally speaking, and we saw that in 210 as well, is that we generally use an array representation of a heap. Now, why an array representation of a heap? Why not just keep it as a binary tree? Why do we have to? It's just a revision. What are the advantages of using an array representation? Yeah. Say that again, sorry. Yeah. So essentially, you said it exactly right, that you don't have the additional overhead of pointers. Okay, it's a really cool and neat implementation of a heap. And as long as you represent it as a complete binary tree, then the array is a really nice representation. Okay, and we sort of saw that in the last lecture, is that this is the array representation. And of course, you don't need pointers. It essentially is very compact, and all you have is you use indices. Okay, and the indices, as we saw in the last lecture, have these nice properties that you can get to the parent, get to the child, and so on, using the following functions. It depends on whether you're starting the array at index 1 or 0. So there might be a little difference between left child might be at 2i or 2i plus 1, depending on exactly where you. Of course, we generally using pseudocode and restarting all our arrays at index 1 rather than 0. Okay, and you should be able to see that the following statement can be made for the indices of the arrays, and that the index of the parent, the contents of that array is always greater than a sub I, and that's simply the heap property, the max heap property. Okay. Now, at what we did study earlier, and we spoke about insertions and deletions in 210. So this is just one of my slides from 210. And what we did was we said, well, if you have to do an insertion, so let's say we're inserting the element 50, or it's often referred to as a key 50. And so if we insert 50, then essentially what we do is we insert at the end of the array. Okay, why is that? What is the logic behind doing the insertion at the end? Again, this is sort of a revision. Why not just insert it at the top and do something fancy with it? What is the advantage of doing an insertion at the bottom? And then we said that we do a bubble up process. Okay, and there are different notations for this. You could call it float up or bubble up, or what have you. So the idea basically is that once you insert it at the bottom, you essentially compare it with its parent. And if the heap property is not maintained, you simply do a swap, and you keep on doing it until the heap property is satisfied. In other words, you, for example, bring 50 all the way up to this particular point where the parent is now greater than 50 and its children, both children, are smaller. Okay, so this was the float up or bubble up process that we've already seen. So what are the advantages process? If you think about insertion, there could have been different ways of doing the insertion, right? And you can think of different ways of doing insertions, but what was the nice thing about doing an insertion using this particular process? What are some of the pros and cons of doing insertion in this particular methodology? Yes? Okay, so a complete binary tree, yeah. Well, I could have said that I could maintain a complete binary tree, perhaps also by inserting it right up here. Okay, and maybe doing something different. So that is a good. That essentially says that we're going to the end of the array, and we're inserting it over here. All right, so when we're inserting a new number, we're inserting at the end of the array, and essentially that does maintain the complete binary tree property, that you're not, for example, inserting it over here, all right, which would have created holes, which would not be maintaining the complete binary tree. So that's one reason. Yes? Okay. Yeah, so that's a good point. So let's say that you're inserting a number This is not a good example, but essentially what you're saying is that, let's say we started putting it at the top, and we sort of said, well, let's make it go down. And the numbers on the left or the right, either one, could possibly be such that it's forcing the number to go down in a particular direction, which results perhaps in inserting it over here. Okay, that might be possible. And if it does do that, while it maintains the relationship between the parent and the child, what is it violating? Yeah, the complete binary tree, which is essentially also saying that the left and the right sides at any point should at most differ by 1. Okay, so we had that over here as well. The height of the subtrees should differ by at most 1. So if you inserted something all the way, let's say over here, right over here, for example, then you could have the right side of the subtree having a different height than the left side. The difference could have been more than 1. Okay, so there are several reasons why this particular insertion that we saw earlier was important, because it was maintaining the properties of both the heap, as well as ensuring that it's a complete tree. Okay, so let's go forward and see what the deletion process was. So deletion, if you remember, essentially what we said was we'll again take the last chap in the array, okay, and move that. So let's say we're deleting at the top, okay, which of course is something that you might recollect we do in priority queues. Okay, so if this essentially represents a priority queue, which basically means that let's say the maximum priority is what we're interested in, and that maximum number is represented by the top. Did a DQ, okay? And when you're doing a DQ, you're essentially saying we want to get, let's say, the patient with the highest priority, okay, or some some application where you want to have the highest priority, and that's represented by the maximum number, okay? And so essentially what you do is you grab the guy right at the top, okay, of the heap, and you remove that, and you've got the maximum value. And then the question is, how do you fill that? Okay, and that doesn't necessarily have to be right at the top. So for example, if for some reason you were trying to delete some key in the middle, then you could delete in the middle as well. Okay, so if it was a different application than priority queues, and maybe you wanted to make some change in the middle, and you remove this particular key over here. And so the question was, how do you replace that? Okay, so what could have been different ways of replacing, let's say, 23 or 52 as compared to what we actually do? And what are the pros and cons? What could have been a different way of, let's say, removing 52 instead of taking the last element in the array? What if we try to do a different operation, and why would that become problematic? Okay, again, going back to just the thoughts that we just spoke about in the last few minutes, similar concept. So what could have been another technique? Okay, so let's say if you want to delete 52, instead of replacing it with this chap over here, let's say what could have been an alternative? Right, you can think of different ways of doing the same process, doing the deletion, but we're just saying this is not the only way. So you need to make sure that there is a reason why we're using the last element of the array to replace the top of the heap or any element that we're deleting. Yeah. Okay, so you could have potentially a lot more to do with that. Okay, do people agree with that? So once you delete 52 and 39 is up here, what else do you have to do? And what would you have to do if you replaced 52 with 50? So let's do a comparison. what would be the set of operations that we'd have to do? Because we obviously, once we delete something from the heap, need to ensure that the heap retains its properties, right? So, so just do the comparison of those two scenarios, okay? The first scenario being what we actually do from what we know, that we actually take the last element in the array versus taking one of the children. What could be the pros and cons of doing those two operations? Why is one preferred over the other? This is mostly a review. Yes.
So if you then you're still going to have to find it.
Okay, can I get your name again? Abe. So Abe has some suggestions, but let's debate that. Abe is suggesting that the number of operations that would be left over would be more in the case where we replacing it with a child versus replacing it with the last element. So think back. Is that true? What do we have to do with 39 once we've replaced it at the top? What do we have to do with 39 once you've replaced it at the top? Yeah. Yeah, so you still have to do that, right? So, and if you had replaced it with 50, what you're suggesting, Ed, is that you would have to do a whole set of operations, but those operations still have to be done with, in fact, there's perhaps a little bit more operations to be done because 39 is now right at the top and you have to bubble it down to make sure that the heap property is maintained, okay? And that would still have to be done if you had replaced 50 up here, okay? So that's not, the reason, if I can say that. Yes. So if I'm trying to understand what you're saying is that you could be replacing, you want to replace from the right, but let's think along the lines that, a few minutes ago, Kyle just mentioned the thought, right? So what are we trying to do? We're trying to ensure that the complete tree, it's still a complete tree. Now, if you replaced it with 50 with one of its children, which was larger, now the heap doesn't have any, the right versus the left, there's no difference, all right? All it's saying is that the parent is greater than equal to its children. So it's possible that, and maybe this is going along what you just said, is that you could be replacing it with, not 50 could be over here, and you're replacing it with the left child, and that would result in maybe one of these guys becoming empty, okay? And that would create a problem because we want to make sure that there are no holes in the array, and that can only be ensured if it's a complete tree. And if you had something missing over here, then it would no longer be complete, all right? Because these elements would then either all have to be shifted to the left somehow, which would be, too much of a problem. So you can see that the technique that is adopted, which was, taking the last element of the array, replacing it with the element that has been deleted, and then bubbling it down ensures that the tree remains complete, okay, and you don't have any holes in the array, okay. Of course, there's one thing that has to be done as well, is that you have to make sure that the size of the array has to be reduced by 1, okay, because now, the size of the array is very important, because that's how you ensure that, where you figure out whether there is a child or not, depending on the size of the array, okay. So that was hopefully mostly a review of some of the things that you might have sort of, forgotten perhaps, okay. And so finally, see, we have a comment over here. right? So what about the complexity? So we did this in 210 as well, and we sort of did an approximate intuitive hand waving kind of an approximation, analysis. And of course, you don't do that in 550, right? So you can see what's coming. So what was the insertion and deletion complexities, intuitively speaking? So if you're doing an insertion over here, let's say you insert something over here, you insert a new number, and then you have to swap things, and you have to do bubble down or bubble up. And so what is the complexities? Okay, so n log n log, is it? Yeah. So Logan's suggestion is that it might be something like that. All right. So agreements for one item. Okay, great. So for one item is just log n. Okay, why is that? Because we're saying essentially, the swaps that you have to do. There's some constant operations like putting at the end of the array, which an array, of course, can be immediately indexed. You can go right to the end of the array. You don't have to go through a linked list. And once you've inserted at the end of the array, then you need to do a swap, and then you have to do a bubble down operation, and that will take at most the height of the tree. Okay, and height of the tree, as you can see, that it's a complete tree. So you can imagine that the height of the tree it's not going to be completely imbalanced. Okay, and so there is the left and the right sides are differ by at most one. So the height of the tree is certainly going to be something like log of n. Okay, so this seems to be correct. And what about deletion? Would people agree with? I presume, Logan, you mentioned that deletion is also log of n. Yeah, and would people agree? Yeah. And so it's a very similar operation. When you're doing a deletion, again, you're doing either bubble up or bubble down, but either one of them will just take it'll be proportional to the height of the tree, and that's log of n. So those are great intuitive responses, but we don't rely on intuition in this course. So we're going to actually spend a lot more time doing the more detailed analysis, unfortunately. Okay. So let's take a look at the following procedure, which is max heapify. Okay, we spoke about this in the last lecture as well. And essentially what we're saying is this is the procedure which maintains the max heap property. And essentially this was the bubble up or bubble down. Which one would this correspond to? Okay. And it assumes that the binary trees are rooted. Okay. That are rooted at left eye and right eye are already max heaps. Okay, so the left and the right. So if you're talking about I being over here, for example, right? So we're saying that the trees in the left subtree and the right subtree are already max heaps. Okay, that's an assumption. So was this assumption made when we were doing a bubble up operation or a bubble down operation? So in bubble up, we sort of going upwards, but here we sort of saying that, we are at a particular point and we're assuming that things are okay below. Okay, so which one of those two operations do you think max heapify would be used in? Or variety, there could be a variety of operations where max heapify could be used. So if you let's say if you're going upwards, would you want to use this? Or just think about when you're going downwards. Let's think about that. You're deleting. So remember when we did a deletion, we said we're going to delete this guy. We're going to replace it with the chap right at the end. We're going to reduce the size of the array. And then what we have to do? We have essentially said that we have some element over here, some key, which is inappropriately located. But however, the heap was earlier a proper heap. Okay. And so the left and the right subtrees were already heaps. So this is clearly going to be used in the deletion, where you're doing a bubble down, okay? And perhaps it could also be used in modifications, and you can think of different ways where this particular procedure could be used. So we went through this in the last lecture. So let's just go through it very briefly and see how this would work. Okay, so we've already seen how this works, but this is the actual procedure. This is the pseudocode. And we're essentially saying that we identify the left and the right indices using the left and right operations performed on a node with the index I. And we compare, and essentially the code is comparing its two children, and it's going to say whichever children or itself, if it's already large, then you don't have to do anything, but if either one of its children are larger, I'm going to swap this particular key over here with its larger child. And then I'm going to do a recursive call on the child that was just replaced, okay? So these diagrams are from figure 6.2, so you can refer to that, and you can see how this worked out, okay? So now, how would one do a more detailed analysis? Okay, so we've done an approximate analysis. We can see that the number of operations are proportional to the height, but in this course, we're going to do a more rigorous analysis. So what are some of the tools in your tool bag that you can use, okay, to do a more rigorous analysis? What comes to mind if you want to do a more rigorous analysis? We've already learned a number of tools. Okay. How would you start off to do a more rigorous analysis? Yes. Yeah. So whenever you see recursion, the first thing that comes to mind is the substitution method, the recurrence relation. Yeah. So if people would agree to that, if you look at the slightly more detailed, essentially the top part is fairly simple, which is theta of 1. It's all constant. There's nothing which involves the size of the heap. Okay, it's only over here where the recurrence is going on, and so you need to find a recurrence relation. Okay, so let's try to see what could be a recurrence relation. So let's assume that we're saying n is the number of nodes of the tree rooted at I. Okay, so we have, let's say we're looking at I over here. Okay, and so we're specifying n to be the number of nodes in the tree which is rooted at I. Okay, and now can we specify a recurrence relation of T of n? So what would T of n be equal to? So what are we doing? Essentially what we're doing is we're doing a swap operation, okay? And once we've done a swap operation, we have now found a smaller problem, okay? So how would you express that in the recurrence relation? Yes? Okay. Does that look right? And would there be one or two, or would there be a multiple? But that is the assumption that it would be just one, simply because you're not it's not divide and conquer. So you're not taking two subtrees, you're just taking one of the subtrees. And so it seems to be approximately Tn upon 2, because you can see that the tree is, generally speaking, it's almost equally balanced. So that's a very good intuitive analysis. And what about, is there some function over here, f of n? And what would f of n be? Yes? So it'll be a constant, so it could be theta of 1. Why is that? Because we just saw that earlier, is that these operations above are essentially constant. Okay, so far so good. Now, in 550, we're going to be really picky, and we're going to say, well, this looks about right. but is it really t n upon 2? Is it really t n upon 2? So let's say you wanted to delete this guy, and is this subtree equal to this subtree? Is it? And it's not, right? Because you can see that when you're replacing it, you could be doing a replacement over here, or you could be doing a replacement over here, okay? But we're doing a worst case analysis. So what are we going to assume? That we're doing a replacement with a swap on the left side, okay? Because the right side is always being a complete tree. The right side is going to be either equal to or smaller. So the worst case is that we're doing a swap with the left side of the tree, okay? Now, if you're doing a left side of the tree, what could be the difference between the left and the right? Okay, so if this is the left side of the tree and this is the right side of the tree, what could be a relationship between L and R in terms of N, okay? So if you say that the tree that is rooted at L on the left side has a size L, and the tree that is rooted on the right side has a size of R, what could be the relationship between L and R, and how would you calculate that? Is it, well, we're clearly saying that L is not going to be, L is probably going to be bigger than R, okay? But what can you express that, and how would one do it? How would one do the worst case comparison? Yes. So you're saying that you Tn minus 1 over 2. Okay. Would that be right? Let's take a look at that. So here we have 1, 2, 3, 4, 5, 6. This is 6. And this is 1, 2, 3. So you're saying 6 minus 1, 5 upon 2, which is 2.5. So you clearly need to have some kind of ceiling or floor function. So maybe if you replace that with a ceiling that seems to be coming out to the right number, which is 3. Yeah. So yeah, you seem to be going in the right direction, and you could figure out the relationship, but you sort of spontaneously came up with that relationship, and I'm not sure how you did that, but how would you do it in a more slightly more analytical way? What's the worst size of the left tree? What could be the maximum difference of the left tree versus the right tree? When would that happen? Yes. The right tree is empty and all the nodes are on the left side, okay? That's a very specific scenario, okay? So that could happen when you don't have anything over here and you have one node over here, all right? And that's a very unique scenario. The other scenario is that you could have, one over here, and this could be another scenario. And the third scenario could be exactly this. So you're in the right direction, but sort of make it more general, all right? So you look at one, the absolute minimum scenario, but in general, what would be the difference? Yeah. 2 raised to the power R plus 1. Okay, so 2 to the R plus 1 would be the left, and this would be to the power L plus 1. So R is, actually, I'm just saying R is the number 6 over here. So sort of going in the right direction, but it's not going to be R in the numerator, okay? So now here's a hint. Think about the heights of the tree. We mentioned that the heights of the tree are going to be at most differing by 1. Okay, so that's a big hint. So once you know that the height of this guy is, let's say, H and HL, HR, and the height of this guy is HL, and we know that if this is H, then this can be at most H plus 1, okay? So we know now the heights of the two subtrees. And when are you going to have the maximum number of nodes in the left subtree? When it is not in this scenario. The maximum is going to happen when it's going to be essentially a perfect tree. Okay, when all of its nodes are occupied. Are you following that? So in other words, the maximum difference is going to be when, in this particular scenario, when you have another node over here. So this chap over here, this entire subtree is now maximally different in number as compared to the right subtree. Okay, and so now can you calculate the size of the left versus the right? Now you can generally say, well, this is height h, and this is height h plus 1. Okay, and if you can figure out what the heights are, and the right one has to be completely filled. Can you see that? Because it's a complete tree. So this right subtree has to be completely filled. It's a perfect tree. The left one, we're saying that when it's maximally different from the right subtree, also has to be a perfect tree. Okay, so now we're talking about the sizes of two perfect trees. One of them is of height h, the other one is of height h plus 1. And now is it simple math to be able to calculate the number in that tree? Yeah. So then it's just a bunch of math. So you can say that this is going to be 1 plus 2 plus 3 and all the way up. Sorry, not 3, but 2 to the power 0 and 2 to the power 1 and then 2 to the power 2. And so you can sum that up and you can find out what the height, what left is. And I think it's going to be something of the order of 2 to the power h, not 2 to the power r or l, but 2 to the power height. Okay. So now we can do that. Okay, and I'm not going to bore you with all of that. So let's assume that we can do that, and let's take a look at the solution. So essentially, what we're saying is that Tn, instead of being n upon 2, we're going to say, well, let's say that this is T of maximum, where max L is the size of the maximum left subtree. Okay, which is essentially what we've done. And then we're saying that in the worst case, that would be following, and you can figure out, here's the example where I'm saying that the height over here is h is equal to 1, okay? And here the height is h is equal to 2. And so you can calculate that the left subtree is going to have 2 to the power h plus 1 minus 1, okay? That's 2 to the power 3 minus 1, which comes out to be 7. And the right subtree is going to have the following, 2 to the power h minus 1. Okay, and then you have to add 1 because you're talking about the total nodes. All right. So if you try to do this, you're essentially saying that it should come out to be. And the next question is, can we show this? Okay, and I've sort of shown it to you that if you work this out, if you have the following expression, 2 times 2 to the power h minus 1 divided by 3 times 2 to the power h minus 1. Okay, that is this expression. When you get expressions like that, you have to look at what are the extreme cases. Okay, and you can sort of plot that out or you can draw it out, but you can say, well, if h becomes extremely large, then this can be neglected, and so it becomes 2/3. Okay, and so you can say that, well, it's either greater than or less than 2/3, and then you can figure out, well, what happens when h is small. Okay, and so that shouldn't take you too long to be able to figure out that it's going to be less than or equal to 2/3. Okay, so we spent a bit of time on this, but it turns out it's not really important whether it's 2/3 or half, but it was useful to do. Okay, and the book does it, and so we didn't really know a priori whether it was going to be important or not. Okay, but this is the actual expression, and we can be a little happy that we were able to sort that out. So now we have a relationship which is less than or equal to rather than an exact relationship. Okay, oftentimes you have an exact recurrence relationship. But if you have less than equal to, instead of using a theta, you would generally use a big O notation, okay? Because then you have an upper bound and not just a theta. So in this particular case, if you go back to your master theorem, all right, so which this is case 2 of the master theorem, you can figure that out. And if you have this relationship, then you can, hopefully by now you can see that through. But if you can't, just look it up in master theorem and you'll see that it is order of log n. Okay, this could have been any value which was, it could have been 9/10 of n. It could be 999,000th of an n. And we saw that earlier, right? As long as you're making the problem a little smaller, depending on what f of n was, you can express it as a logarithmic expression. And I'm not going to go into too much detail on that, but we should be able to see that expression and to be able to say, yes, it looks like a log n. And you should be able to visually see if you're doing a recursion tree, why it's a log n operation. Okay, so if you're not seeing that, just go back on your notes and make sure that you can now see that. So now this is one way of expressing it, that T of n is order of log n. But a more useful expression that we're going to be using as we go down in the next few slides is the following relationship. Okay, and this relationship says that instead of saying log of n, which is in terms of the number in that subtree, we're going to relate it to the height of that node. Okay, so if h is the height of the node, so let's say if we're deleting this particular node, okay, and then we're doing a max heapify over here, or for some reason we're doing a max heapify on the node I, and the height of that particular node is h. So h is not the total height of the tree now. H is now the height of the node, which is the one that you're applying max heapify on. Then you can see that T of n is also big O of h. Okay, because we can see that h and n have the log relationship. Okay, so now this is the equation that we're going to use as we go forward. Okay, so whenever you're going to apply max heapify on any particular node, then it's the complexity is big O of the height of that particular node. Okay. All right, so that was the first part. Now, what about complexity? Okay, sorry, the complexity of doing multiple insertions. So let's say that you want to build the entire heap. Okay, and you want to do it one element at a time, one key at a time. So how long would that take? And I think Logan had a response to that earlier. And you said that if it was one element, it's going to be log of n, but if it was n elements, it's going to be n log n, simply because now you're sort of building up the heap one element at a time. And as you can sort of intuitively imagine that as you get to bigger and bigger heaps, then each of those operations is going to take log n. And because now you're multiplying it by the total number of times that you had to apply, so you can see that it's going to be an n log n operation. Okay, so for n insertions, it's going to be n log n. Okay. However, what if the elements, is there a faster way of making a heap? And again, we went through this in Heapify. We went through this in 210, and I mentioned the function that we used, sort of a name of function that we used, but we didn't really go through that function in a lot of details. Okay, those of you who were in my course last semester, we sort of did that in one of the assignments, and we said, well, assume that it can do it in this operation, and it's going to be less than n log n. So how much time did that take? And what were the conditions in that? So we weren't building up the heap step by step. What did we say? You have the entire, let's say you're getting that data from somewhere, okay? You have all of the data together. Okay, you don't necessarily need to create the heap one step at a time. So if you have all the data together, let's say you have the example I think that we said was, let's say you have some medical data and you have patients' data, and all of that data has just been transferred to your medical university, and now you need to convert that into a heap. Okay, so now you have all the data in a lump sum. Okay, so now can we create a heap in a faster way as compared to doing it piecemeal, which is n log n? And does anybody recollect that? Can you think of a better way to do that than n log n? Okay, so these were the steps that we're doing in piecemeal, is that every time we added. And why would you think that we can do it faster? Yes, the lady in green. Yeah, that makes sense, because why do we need to actually do it piecemeal, right? Because we're not utilizing the heap as at every step. So why do unnecessary work? Why not just create an arbitrary heap, not a heap, but actually put it all into a complete tree and then apply the algorithm? Because we're not really utilizing the heap in the middle. All right, so that's the idea. And so this is what we're going to do, is we're going to use a procedure called build heap. And that's what it's going to assume, is that we have all the data at one go. Okay, and now we're going to apply, either a bubble up or bubble down, all of those procedures to be able to figure it out. And as you can imagine, we didn't spend too much time on bubble up. We spent more time on bubble down, which we said was heapify. So you can get an idea that we're probably going to use heapify. Okay, which is essentially saying that we create the heap. Okay, and for every element, we're going to sort of now bubble down. Okay, so let's take a look at this particular procedure which adopts that. Okay, so it's build max heap or build heap. Okay, so it produces a max heap from an unordered input array. Okay, so you put all the data into an unordered array. There is no heap property in that, but now you're going to use the build heap on top of that. Okay, so once again, how would you do that? So I've already given you a fair amount of hints, but now I want you to think about it. How would you actually, and I think that was Jane, I think, who suggested that. So Jane, can you give us some steps as to how you do that? So we start from the bottom and then we go upwards, sort of like that. All right, almost like that. Why from the bottom up and why not from the top down? I'm not saying you're wrong. I'm just saying why not? What can you see a reason why going from bottom up would be better rather than going top down? Yes, Scott. And you can also see why heapify comes in more handy, right? Because what did heapify say? Is that we are assuming that the subtrees underneath you are already heaps. And so if we start from the bottom up, as Jane suggested, then we're essentially creating little heaps underneath, okay? And then as you go upwards, we can use heapify, and that can be applied because it assumes that the left and the right subtrees are already heaps, okay? So great. As opposed to, let's just think out loud. What would happen if we try to have a different approach and we said, well, let's take a look at another approach. Maybe it might be better. I mean, you can surprise yourself. What if we start from the top down? Can somebody figure out what kinds of issues might that create? And would that even work? And if it would work, would it be more complex? Yes. So you would have larger values in the middle, okay? Yeah. So essentially what you're saying is that, if you have the wrong number at the bottom, you may have to, the number of steps seems to be more complex, okay? We don't have an exact expression as to compare, so you could come up with your own algorithm, which says, well, let's apply a top-down approach, and let's compare what is the complexity of the top-down versus the bottom-up approach, and it could be an interesting piece of research, as you might say. Okay, so we're going to use the bottom-up approach, and I think this is where we sort of were in the last lecture as well, where I think Carl, you mentioned that we could, and James, you've also mentioned that we could start from node number 16, which is, and the reason, as we saw, is that these nodes are already leaves, okay? And any leaf presumably is already a heap, okay? But because it doesn't have any children, so it's already greater than its children, right? And so you could start with this particular shaded node, okay? And the question is, if you know the size of the array, can you figure out the index of the node which has the first child? You could think about it, maybe you could come up with an expression, right? It can probably be calculated, okay? So it can be calculated, and this is the following expression. It's basically dividing it by 2. So if you, let's say you have 10 over here, you divide by 2, and you take the floor of that comes out to be 5. And so in this particular example, it works out. And you can see sort of, if you work with a few examples, you can see that that's the spot, that's the index of the node where the first child appears, okay? So you don't have to start all the way from end, you can just start from midway, okay? And then since we're working upwards, we're working backwards, so we're going to start with this particular node, okay, at index 5, and we're going to apply heapify, okay, because we want to convert that into a heap, all right? And once that is done, we go to the next node, upwards, okay? And we go to number 2, and we convert that. So 16 happens to be a heap already, but 2 wasn't exactly a heap, so we swap 2 with the larger number, larger key, which is 14. 14 comes up here, and 2 goes down here. And so now we have this subtree is now a max heap, okay? And we don't have to worry about anything else. And then we go next up, we go up to 3. 3 is clearly not a heap, so we replace it with the larger value, which is swap these 2 guys, and you have 10. And now this is also a heap, okay? So these, each one of these smaller subtrees are becoming heaps, and then we move to the next index up the ladder. And so this one clearly has a problem. So what are we going to do? Well, we're going to see, well, which one is larger. So 16 is the larger number. And so we're going to swap 1 and 16. 16 comes up, and then 7 is still larger. So 1 goes all the way down. So you can see we start doing a max, that heapify or a bubble down operation at each level. Okay. So it's still a fair number of operations. It's still not trivial, but we can see that we're applying the heapify method because everything that has been seen earlier is at a higher index of the array, and all of those have already been sorted out. They're all already heaps. Okay. And eventually we get to the top, and that's when we stop. Okay. So this is the procedure for a max heap. And now the question is this any better? Is this better than n log n? You're still doing a lot of log n operations, and you're still doing it n times. So why is it actually better than n log n? Yes, Carl. Yes. So essentially what you're saying is that there are two kinds of operations going on. And it's not completely obvious, okay? Because you'll see another example, a counter example of this, where a similar operation is done, but it doesn't come out to be any simpler, okay? So this is the case where you're starting off doing operations which are initially log of n, but those are extremely small. So you're starting with small numbers, okay? And then it's becoming bigger and bigger. And as it's becoming bigger, the other operation, so essentially we were doing the number, the complexity of each operation times the number of times, okay? So it was multiplication of two things. Complexity of each operation times the number of times you had that operation, right? So now what we're saying is that the complexity is building up, but initially the number of times that you did it was initially very small, okay? So as this operation is building up, this is going down, okay? So it's kind of a, it's not completely obvious that it's going to become, it's actually going to be a simpler operation, because a lot of examples, if it wasn't this way, okay? If it was the other way around, for example, you started off with the number of operations slowly growing and the number of times also growing. In that case, it wouldn't work out, okay? So, so that's the intuition. So now we need to, in 550, obviously, go through the motion, okay? All right, so first of all, let's take a look at the correctness of this algorithm, okay? So can people think of the loop invariant? Can you think of a loop invariant which would sort of prove the correctness of this algorithm? Okay, so it's a reasonably simple algorithm, okay? And if you think about, yes. All children at location I, let's say you're operating over here, okay? I is right over here, okay? And what you're saying is that, can you repeat that? Sorry, I missed you. Okay, yeah. So can I get your name again? Thomas? Sorry? Thomas, okay. So Thomas is suggesting that all the children at I are already max heaps. Okay, all the children, so if you are operating at a particular index I, then all of its children are already max heaps. Okay, so anybody like to agree, disagree, or expand that thought? So Thomas is very particularly saying all its children, okay? So is that good enough? Think about another example, okay? Let's say I is over here. So, and its children are these guys. And you're saying all its children are max heaps. Is that all you can say? I mean, that's correct, but is that a good enough loop invariant? What are you neglecting? So as you've gone forward, as you've gone this way, and then you've gone up the index, all right? And then you're going this way, right? So when you are at this particular location, let's say you've done this. Well, these guys have already done. You've done this, and you over here, right? So again, a hint. You're saying only its children are max heaps. So Thomas is saying only its children are max heaps, but I'm saying that you can say more than that. right there. Yeah. All children of whom? So this, are you saying that this guy is also max heap? That the entire thing is max heap? That doesn't sound like a loop invariant. Loop invariant says that at every I, at the beginning of every loop, you want to say something which is going to be true for that loop, and then you've got to do the maintenance and so on. Yes. Okay, so now you're sort of getting at something. Now remember, the loop invariant is something which is true at the beginning of a loop. Okay, so your statement, Thomas, about at the beginning of the loop, that at the beginning of, let's say, a loop, when you're over here, you're saying that its children are already max heaps, which is perfectly fine. I think you, Raj, has said that you not only look at this particular node's children, okay, but you've also done this, right? So you've already created an index I plus 1, or any index which is greater than I is already a complete max heap. Can you see that? So once you add particular index 2, okay, 3 is now rooted at a tree which is now has already been converted into a max heap. Why? Because we're going upwards, right? And as we're going upwards, then we're converting for at every I, we're converting that after we're done with that entire loop, that particular subtree that rooted at that index I has now already been converted into a max heap. Then we decremented I, and we went from I being is equal to 3, and we went down to 2. And so we're not only saying that its children are max heaps, but all trees rooted at greater than I are max heaps, okay, which would include its children as well, okay? So indices 3, 4, 5, 6, 7, 8, 9, 10, all the way till the end of the array, all of those are essentially already have been converted into max heap, okay? And this was basically the concept that Jane had suggested, is that we go upwards, okay? And by going from the last index, decrementing the indices, you essentially said that if we're operating at index I, then every tree rooted at I plus 1, all the way till the end of the array has already been converted into a max heap. Okay, so if everybody agrees with that loop invariant, we can go forward. Agreement? All right. So here is the loop invariant. We're saying that at the start of each iteration, the for loop, all the nodes, each node's I plus 1, I plus 2, all the way up till n is now a root of a max heap. Okay, so that was the loop invariant. Now let's go through the motion initialization. Can somebody convince me as to whether it's true at the initialization stage? So we at the initialization stage, we've picked the first node, which has a child. So why is it true at initialization? Why is the statement true at initialization? Yes. Yeah, that was, where we started off by saying that, if you don't have any children, you're already max heap. Okay, so initialization is sort of trivial. What about maintenance? So can you sort of state that out loud as to why would this be true during maintenance? Why would this loop ensure that as you're going through that loop, once you're done with loop I, and you decremented I to be I minus 1, then the same can be said for I minus 1. It's kind of almost, some of these things become almost trivial, but you know, you have to express that triviality. So we've already done that operation at a particular node. Okay, so let's say we've done that operation over here. Okay, and we've already converted this through max heapify, and then we've decremented I to I minus 1. So clearly, everything above has already been converted into a max heap, right? I mean, it's not saying much. So, and the other thing that's important is that everything underneath it was also a max heap. Okay, so you can go through this, but it's kind of trivial. And then finally, the last stage, termination. What happens at termination? So is it going to terminate? Yeah, it's clearly going to terminate because it's a for loop and you're not changing the value of I. It's going to go all the way down to 1. And so you can see that once you get to terminate it, it's kind of obvious that everything now has been made into a max heap. All the indices which are rooted at indices 1 and above are now max heaps. Okay, so that was a little bit of a effort, but you know, it's important to be able to get loop invariants under your belt, because that is an important part of this course, and to revisit it once in a while. Now let's talk about the running time. And now we've sort of already seen intuitively that it would probably be better than n log n. Okay, but the intuitive answer, the initial answer was that, well, if you do it in a very trivial kind of way, it seems to be n log n. Okay, because you have log n operations at every height. Okay, at every point, and you're doing n operations. Okay, but clearly, as Kyle had mentioned, that there is probably, you can do it better. Okay, it probably has a lower complexity. So now what we're going to do is, we do have a few minutes left, so let's try to go through this proof. And what we're going to do is the following steps. So we're calling max heapify, and we've already said that if you apply max heapify at a particular node, then the complexity is proportional to the height of that particular node. Okay, so that is done. And then you have to multiply it by the number of nodes at that height, because they're all going to have the same complexity. Now, what is the number of nodes at a particular height? Okay, now remember the height is growing from 0 at the bottom all the way up till the maximum height of the tree at the top. Okay, so at a particular height, what are the number of operations that you have to do? Okay, so you have to heapify over here, then you've got to heapify over here. Let's say if it was a larger tree, you would have to heapify a number of times, okay? And that would correspond to the number of times that you're calling it, okay? So can you give an expression? And you can see that it's going to be inversely proportional to the height, okay? And it's going to be inversely proportional based on the power of 2, all right? And that's kind of, you can verify that when you have height of 0, okay? So n divided by 2 to the power 0, which is 1, would basically mean that you have n, n, you're doing it approximately n times. So this is an approximate expression, because if you dealt with all of these floors and ceilings, it doesn't really help. It just complicates the solution, okay? So that's done in the book, but I'm going to use a slightly easier set of operations to be able to prove this, okay? So I'm going to say, well, n divided by 2 to the power h plus 1 is, and the ceiling of that can be approximated by n divided by 2 to the power h, okay? And this is going to suffice, believe it or not. So, sort of reverse engineering it. I went forward and I said, well, this is simpler, so let's just remove the complexity. Okay? So now let's take a look at the overall complexity. Okay, so this is what we were talking about earlier, that the total complexity is for each node which is of height I, okay, you've got to take the cost of heapify at that node, okay, which is clearly order of h, and then you have to multiply it by the number of nodes at height h, okay. And as Carl had mentioned earlier, is that as we go from h is equal to 0 at a 0 height, we keep on going upwards. The number of nodes is, while this operation is very small, okay, this operation is very large. Okay, the number of nodes at this particular height is large, but it's becoming smaller. Okay, so the number of times you do multiply O of h is becoming smaller, but O of h, the number of times is going to become smaller, and O of h is going to become bigger. Okay, so starting with this expression, let's go forward. So now this is clearly order of h, and we've already seen that the number of nodes at height h is inversely proportional to the power h. Okay, now can somebody just look at this and try to see what the result would be? The mathematical geniuses amongst us, can you look at this and sort of say, well, what does this look like? Is this going to be order of n log n? Is it going to be order of n? How can you just look at it? You know, there are some geniuses who can just look at expressions and, you know, answer pops out in their head. Here's one. Sorry? Okay. So okay. Yeah, so that wasn't exactly a mathematical genius statement, but so one of the things that you can immediately do is take this n out. Okay, so now you have n, and you have order of h. So let's express that as h.